actually very pleased to see a lot of people here, which is fantastic. We have, I think, one of the more abstract topics in this track, so it's quite nice to have a little bit of a change from the technical stuff sometimes as well. I am, however, a technical person, just to be okay, so the principles and best practices, and first of all, would like to introduce you all to Swiss Re, for those who do not know. We are one of the world's largest reinsurance companies, meaning that we offer insurance to insurance companies. This is really a thing, and it's been going on for a long time now. 1863 we were founded, with 14,500 people. Our motto, our mission is to make the world more resilient, meaning when catastrophes happen, we're there through the clients that we serve to bring people back onto their feet. And we're talking here big catastrophes that single insurance companies themselves cannot cover. So we're there to help out the insurance companies to get people back on their feet. And of course, we are a scientific community, engineers, actuaries, and risk modelers. And as you'll see, this forms a major part of the culture of what we need to do as data scientists in the company as well. So, as a little question on motivation, just like a quick show of hands, who here is a practitioner, like a data scientist, who's building machine learning models and perhaps putting them in production? Okay, it's a good spread. And who here is a manager of teams who are involved in doing this kind of stuff? We have also quite a few managers here as well. Okay, so how many of you practitioners and managers have created machine learning models and noticed that there was a mistake in them at some point? Hoping to see pretty much the same hands go up. Exactly, everybody. Everybody is making mistakes, and this is part of course, innovating and doing something new. And of course, also the fact that what we deal with is very complex stuff. Okay, so how many of those hands that went up, how many of those mistakes also were found out after the models or systems were put into production? There should still be a few hands. This happens. Of course, we saw a few real-world examples in recent history. There's the famous Wall Street issue that went on here. There was a specific model that was designed to predict prices of options, and at some point this model was making assumptions that in the stressed financial times of 2007-8 no longer held. And those assumptions led to wrong prices and a spiral of bad pricing. It wasn't the fact that the model was even badly designed, but rather it was badly used. The assumptions were not correctly communicated, and the model was being applied in situations where it should not have been applied. Or even a much more recent example, and a very sad one of course, is that even this isn't a machine learning model, this is a software system. But erroneous angle of attack measurement led to wrong inferences being made, wrong results being communicated, and unfortunately many lives lost. Of course, I don't know about everybody's industries here, but in the insurance industry we also have big risk of communicating wrong insights and wrong decisions based on models, or indeed using models wrongly. And so we want to make sure that we're not one of the reasons why headlines are written about this particular AI machine learning model caused some catastrophe to be wrongly addressed, or led to losses of lives, or anything like this. We don't want to be in the headlines for that, and I think none of you do either. Well, hopefully not. I mean, they do say that infamy is the quicker way to fame. So anyway, I'm going to work on the assumption that everybody here is trying to essentially protect the results of their work, in the sense of we want to be sure that what we do has good validity, good accuracy, and is performing as is intended to do when we're dealing with very complex things such as predicting the future from historical data. So of course in insurance we have some specific requirements, particularly we're very interested in uncertainty predictions. So rather than just predicting the average age or the expected life expectancy for a particular policyholder, we rather want to know what's the uncertainty of that prediction as well, because we need to then put that into a pricing model. We, of course, we do know that in the modern age now we have machine learning models instead of just complex actuarial models. We now bring in additional expressivity and complexity. And these require additional safeguards. And as it says, we also have additional oversight and correctness cultural priorities within the insurance industry. So as a data science team, we really need to be sure that we're ahead of the game with regards to making sure that our models are correctly, accurately deployed. One of the key points at the bottom here is that we decided very early on that as we were defining how we want to basically professionalize our work, we decided that we wanted to do it as not a set of checklists and rigorous safeguards that somebody must check, every single box must be ticked. Rather, we want to set up principles which the culture should then be encouraged to follow. Of course, this still needs to be enforced in some way, and what we then set up is a peer review board, which is applying those principles on projects at the time when it's about to go into production. So, of course, these principles have been applied, hopefully, throughout the development lifecycle of the project, but by the time it comes to making a decision about go or no go, we have then a list of principles that will be used as part of the evaluation in a peer review setting. So that means that people who created the project are first documenting everything, making sure that everything has been explained and thought through. And even the process of doing that, by the way, in that process we come up with a lot of times where people realize, oh, we missed something there, we made an assumption here that is wrong, just in the process of documenting. So the peer review board is more like a final sign-off, assuming that everything has already been hopefully correctly done, but we're there still to check that at the end of the day, only good models are going into production with full understanding of how they should go into production. So yeah, we want to make sure that we are using models properly, and we also want to ensure that our data science community is collaborating with one another to peer review continually, to check each other's work according to these principles, which I will shortly outline. And then at the end, we do have this peer review. Okay, so the principles themselves, we've realized they can be split into 4 different kind of categories. What we did was actually bring together a number of people from around the business who are practitioners, some from risk management, some from the core data science team, some from other data science communities around the company. Like I said, it's a big company, and we wanted to bring that diverse view, still insurance biased perhaps, but this diverse view, and we came up with this set of principles as a ground-up exercise. And the reason we did that was also to build ownership. The data science community itself, with its expertise, putting together the principles by which we operate. And I think this is actually kind of important because, yes, there are external companies, Google, for example, OpenAI, I think, putting together also sets of principles, and these are good, of course. We wanted to make sure that we reference with these things, but that these are our principles, that we own them. So from that point of view, what I will now do is go through some of these principles and some examples of how they would apply. But I want to be clear, you're welcome to be inspired by these, but if you decide to go down this route, I would strongly encourage that it's something that involves the data scientists and is built from the ground up. By the way, for those who are taking notes or photographs, I think the slides will be available later. So feel free to take pictures, but don't worry about catching everything. Okay, so with no further ado, and there's a lot of text, again, I'm not going to go through everything, but I just want to give some examples. On the choice of appropriate data features, this of course is a data-related principle. And we want to be sure that we are always picking data that is appropriate for the task in hand. So as an example, age is up there. In some cases, for some industries, for example, age may be something that you really should not make judgments based on. For example, HR screening, right? So at some point, this is going to get you into trouble if you have age as one of the features in a model. On the other hand, for pricing a life insurance policy or a car insurance policy, age is absolutely important, right? This is a fundamental factor. And of course, there's the famous example of discriminatory features as well. So there's a story from US insurance where social class was, well, a proxy for social class was the credit score was taken. And this turned out to correlate, I can't remember in which direction, but it did correlate with car accident rates. And as an insurer, you want to use the data that's available, but as a regulator, and indeed as perhaps an ethical person, you also want to be sure that you are not unfairly treating people based on factors and influences. So data quality, and I think, I'll refer to my notes now. Data quality, we have, again, some famous stories there of making sure that the data is correctly referring to reality. So one example is when, I think it's still the case, if you search in Google Images or in Bing Images for a picture of babies, what you get back, at least at the time I last did that, was only babies ethnically white. Right? The reason being not because Google is, or Bing is racist, but because data has been provided and has been learned in an unsupervised way, and a category of babies was labeled as these are babies. It's correct. But of course, the algorithms themselves are making differential decisions based on, okay, this is belonging to the category and this is not. And there could well have been categories for babies of other ethnicities, but these were not labeled as such. So the result of the algorithm is that it looks like it's making racist-based or racist assumptions. However, it's because of wrong use of data. When talking about feature engineering, of course, we need to be very careful about things like target leakage. So an example from a previous company that I worked for, predicting churn of customers, and JP, I think, be very familiar with this one, as I think you originally worked on the model. I think that's correct. But okay, anyway, the problem wasn't what you did, the problem was what we did. We were bringing new features into the model, and we realized that the communication of customers with the company was predictive of whether they will churn or not. Except that we actually got a very, very good score of accuracy on our model. It was close to 100%, and then the alarm bells start ringing. It shouldn't be this good. The reason it was so good was because actually one of the types of communication that went into that model was the intention to churn, the intention to leave. So of course, if you have that data, you're going to make the prediction completely correctly. So that's target leakage, and you want to make sure that it's not in there. On the model development itself, so you've selected your data, you've hopefully got some good representative data of your problem. You want to be sure that your model is developed correctly as well. So one thing that we could look at in insurance is that trying to predict the specific outcome on an individual level is incredibly hard. Okay, so you might say that you have a life insurance policy, trying to predict that that person will pass away on a specific date. You're just not going to get an accuracy measure there that's any use. So rather, as a performance metric, you would not take accuracy on individual predictions, rather you might take a group and look at the rate of mortality over a certain time. It's about picking the right metrics there. And on validation, again, we want to make sure that that we're dealing with something that's in perspective. So just saying that my model has 95% accuracy doesn't really help if there is an 80% chance of the true glass case happening, right? So let's say that there's a possibility of customer churning, and this is in a certain group with 80%. Well, if I've got 95% accuracy, this is not so impressive. So we want to put everything into context. Also, of course, with calibration, the underfitting and overfitting thing, I think this is a fairly self-explanatory one. We want to be sure that models are trained such that they are able to perform on unseen data. So, of course, as a practitioner, you know you've got to hold some data back and then train the model on only some subset of the data and test it later on the unseen data. We'll move on to some usage things as well. With the fit for purpose, this is of course a very key thing. We heard earlier about explainability in the previous talk. Not all models need to be explainable. in the sense of you need to understand exactly how a decision has been made. Take, for example, a previous project that we've done in Swiss Re, which was, believe it or not, to classify the muzzle, the nose and mouth region of cows, and to compare sets of images of cow photos, right? So this is a specific claims handling procedure if you've insured your cow against disease or death. That model needs to be accurate, but you don't need to know necessarily every internal neural firing to understand that. Compare that to a model that is pricing a specific life insurance policy. There it has to be explainable. Why did the model come to a decision for this particular person of that particular price? So we're covering in there the usage principles. This, of course, is very important in relation to the Wall Street example that I gave earlier as well. If your model is explainable but is incorrectly used, then you're still going to end up with problems. You also probably need to have some form of recalibration or retraining of the model going on at regular times. And this can be done in an automated way. AutoML is of course growing in usage within companies. Whether it's automated or manually done, it needs to be checked. There needs to be oversight that says that if there is a process for updating a model, that it is also, the performance over time is tracked. And for change management, this one, of course, is a very human-related thing. Okay, so for those of us who are putting models into production, change management is a challenge, right? So a lot of people in older industries, in particular, like in insurance, where existing models are already doing the job in some way, and we're coming now with new techniques. Trying to get that buy-in is very important, and trying to make sure that the business processes are taking the right usage of the models, again, is very, very important. And again, communicating the limitations of a model. It's all very well coming with an all-singing, all-dancing deep neural network that does predictions for a specific subset of the population, but if the people using that model are using it or abusing it for types of data that it was not designed, or situations that it was not designed to predict for, such as the Wall Street example, then there will again be problems down the line. So this is as much an internal check as checking that the communication to the end users has been done correctly. And finally, on the principles, we are very, very interested, of course, in auditability. And insurance is a highly regulated industry, as is, of course, banking. And to ensure that our models have been developed in such a way that the development process can be tracked, that means you probably need to bring in version control and software checking if you haven't already got something like that, and documentation. Like I said, the process of the data scientist documenting as they go and putting that into tangible form, that is actually a significant thinking point for the data scientists to then discuss with one another if every assumption has been made correctly and if things have been done in a way that can be put into the business, into production. So those were the 13 principles, and like I said, we have a peer review board that then evaluates each project on the basis of these principles, and at the end of that we should at least be confident that our work has the right quality to be used in the business and to gain the trust that is needed to actually really perform. Of course, like I said, this is not a solo journey. We have a number of collaborators here, so Jörg is the colleague of mine, also presenting in Zurich today, and then people from around the business in various different engineering and risk modeling groups. So, like I said, to summarize, we've brought together from the ground up a set of principles that we then buy into, because this is driven by the practitioners themselves, and this gives management and business the confidence to know that the work that we do has high quality. So I'm ready to take any questions. I think time is actually just about out.